everyone, welcome to the third coding tutorial of neural networks and deep learning. My name is Everly and I will be teaching in today's tutorial. So coding tutorial 3 is broken down into two parts. The first part we will talk about PyTorch, and the second part we will talk about visualization. So in today's tutorial, we're going to teach you how to use PyTorch to build neural networks. PyTorch is one of the deep learning frameworks in Python, and another framework you might also hear and see a lot is TensorFlow. And so here's a quick comparison between the two frameworks. PyTorch is more of a low-level language, so it gives you more flexibility to customize your own code and then define the details of the models, data, forward, backward mechanism, etc. And on the other hand, TensorFlow is more of a high-level language, so it's easier to use and friendly to beginners. And it also has some good visualization tools incorporated. So PyTorch is usually preferred by researchers, and TensorFlow is more often preferred by industry. And today we'll start with introducing you how to use PyTorch. Um, Before today's tutorial starts, don't forget to copy a file, save a file in your own directory so that you can make changes to the script. So in this tutorial, we will first start with introducing what's tensor in PyTorch, and then we will create some sample data set using tensor as a holder, and then we'll build a MLP model, and then after the model is done, we'll initialize and then define loss function. And finally, we will apply optimizer and then train the model. Okay, all right. So with that, we will first start with importing the package. To import PyTorch, do torch, and we can also do torch.nn, which is NN refers to neural network. So here, because torch.nn is going to be used a lot in our code, so I just import it as nn for simplicity. And the first part, let's start with tensor. So tensor is more like an array holder. We can find torch NN documentation here. And if you want to learn more about what tensor is, you can go to here, torch.tensor. So basically, it's like a multi-dimensional matrix. If you're familiar with NP array, it's very similar to that. So here we can use a tensor to store our data, and let's start with calling torch.tensor, and I can just throw in a small matrix such as this, and we can print the tensor. Okay, so now we get a 2x2 two-dimensional tensor here. And in addition to that, Torch also offers us to initialize a tensor with all ones. So let's say we call torch ones, and then assign a shape to this tensor. This is just a random example. And again, print it. Now we have a tensor. Its shape is 3 by 2 by 2. And all these elements, we didn't have to assign all the elements manually like we did in the last cell. All the elements when you call once is assigned as ones. So let's move on to the next part. We can also initialize a tensor that is sampled from a normal distribution using this function here. You can check this link out to see what parameters are available here for the randomization. And with the just simply calling it, we can do torch dot random like input x, and let's see what the output. Okay, so here's the result sampled from normal distribution. We will use this as a noise in the next part. So part two. Now we're going to create a sample data set for the model that we're training later. First of all, start with creating a y, which is the ground truth, as all ones. And for this data, we will do 10 sets of data, and for each data, there are 5 features. So y will be a 10 by 5 tensor with all ones. And now, let's generate the training data x. In this task, we want our model to learn how to predict the original data um, from the data that's added noise. So we will just simply add a distributed noise to y, which is the ones, to create x. So from this x set, we want the model to learn to denoise x basically and find y. So let's name it x train again. That would be y plus the random, that is the noise with all ones. And this is the train set. We can create the test set in the same way. So the distribution is the same. Oops. And with that, print y to check. So y is all ones with 10 by 5. And we can check out x train. So x train is the same shape with noise added to the data, and test set. Test set is the same distributed noise added to y, but a different set from train. Now we have all the data, we can move on to building a model. And today we're going to build a MLP model to define a model in PyTorch. Let's go to NN module class. So this class is the base class for all neural network modules. So basically, we can just follow this example to create our own own neural network model. So I copied the code here. As you code, you can check out the example and build your own customized model. So let's start with defining a class. Call it multi-layer perceptron model. And following the sample code, we need it to inherit from the base class. In the initialization function, we need to first call the base class. So what we should do here, is call the initialization first. So this makes sure that our new class inherits everything from the base class. And then we proceed to this part would be to, oh, sorry. Before this part, we need to make sure that the input, the initialization parameters input here are saved. So let's do the input would include the input size. And also, we want this model to be adjustable in hidden layer size. So, and we save these parameters here. Okay, so now the parameters are saved. We can move on to defining the model layers. And in this example, we will create two linear layers for our MLP model. Now we start with the first linear layer. We can call it linear 1. And for linear layer, you can check out the PyTorch documentation. They have linear layers. There's recurrent layers or convolution layers. Today we're just going to use this basic one, and there will be the size of the input features and the size of output features. So we can call linear, and the input size for this layer, because this is the first layer and the data has just been input without any other process. So that means the shape of this layer would just be the input size. And the output size here is where we allow this model to be adjustable, which is the hidden layer size defined upon initialization. Okay, so that's the first layer. And after that, we need an activation function. Call it activation 1. And then we can call activation So you can check out, there's a list of activation functions available. And here, let's use value. And then um, the second layer would be linear 2. And again, we call NN linear. And now, so the input for this second layer would be the feature output from the first layer. So that means the input size would be this. And the output size is for us to decide, but for this model, because we're only building 2 layers, that means this is actually going to be the exact output size. And for this task, the shape of the input is equal to the shape of output. So we're just going to use input size as the output um, size here. And then again, we need activation, call it activation 2. And we can try sigmoid for this one. Okay, and that's all for the layers in this data set. We can move on to the next part, which is forward. So forward, self, and x. X would be the input here. So the thing we should do here is to go through all these layers, make sure that the features are fed forward. So for the first step, we should call linear. We can call the output of the first layer linear 1. Call our layer. And input would be x. And then activation. The input would be this previous output. And then linear 2, we again feed the previous output from the first activation here. And then since this the second activation function is the last layer, so this would just be output. But you can name it whatever you'd like. But this is going to be the activation 2. This is going to be the output of the whole model, and finally return the result. Okay, so this is going to be our model class. And part 4, we can move on to initializing this model that we built. And also we can define a loss function. So first of all, we can just call it model. And initialize it with input size and hidden size. In this case, the input size would be the feature size, which is 5 for this data set. And the hidden size, we can do a very simple model with just 3 size 3 for the hidden layer. And with that initialization, we need to define a loss function. And here, for the loss function, we can call from PyTorch. So here are a list of different loss functions that you can use. Today we're going to use binary cross entropy as an example. So, um, call NN, and that would be our loss function. So before this model has been trained, it is only initialized for now. We can see how the model is doing. Predict an output, and we can feed the model with the training data and print out the prediction. So this is the current prediction, and let's see what's the current loss from um, now that we have the prediction as well as ground truth. We can do apply loss function fed with the prediction as well as ground truth, and see what's the current loss. Okay, this is the loss we get for now. So with this loss, we can also check out what's the model weights. And we can do list name parameters. For this, you can go to NN module documentation to check out what are the parameters, what are the functions you can call for a model. Run this. So for this model, we have these weights that include linear weight, linear one weight, linear one bias, linear two weight, and bias. So that's all the parameters we have in this model. And okay, so now let's move on to part 5, model training. To train a model, we need to define an optimizer. And to check out what optimizers are available, you can go to this link. So I already copied the sample code from this link. So you can see that to initialize an optimizer, you need to do something like this. And to take optimization steps, you can code something like this. So we will just follow this. First import the optimizers. And we can start with initialization. I'll use Atom for this example. And then we need to input the model parameters. And here we will set the learning rate. So now we can move on to training the model with the optimizer. Let's run 10 epochs. Okay, so in this, for each epoch, we need to do these steps. So let's start with this. Um, set the gradients to 0, and then we do a prediction from the current model weight. And calculate the loss with prediction and ground truth. And then we do the backward following this, compute the gradients, and eventually optimize it. And that's all the steps required for this. Now we can print the current steps. For the epoch, we print out the training loss. Okay, so we can run this cell, train the model. All right, so from here we can see that the loss is decreasing as we train from epoch 1 to 10. Now that's everything you need to know about building and training a model. Now we're just going to quickly print out the results. Predict the so now the model has been trained. We can predict from X-train. So now the ground truth is all ones. So after training, we can see that the model is almost there, guessing all the results one. We can also test it on the test set. And it also performs pretty well. And that is all. A quick review. I recommend you read through the PyTorch documentation to learn more about um, what you need to know about PyTorch. And today's tutorial, we covered an tensor. We covered module, which is the base class for the models. We practiced how to build our own model with layers such as linear, with activation functions such as ReLU and sigmoid. And we also apply loss functions, which is, for example, BCE loss in our case, and optimizers, where we used Atom as an example for your network. And that is all for today's tutorial. This tutorial is adopted from this link. For a longer version of PyTorch tutorial, you can visit this link and see their code. You're welcome to stop by my office hours or leave your questions on PS.